Hi, my name is Amit Jain. I work for Intel Corporation. I used to work for Peregrine Power, which is where I did some work on the dual active bridge converter. I apologize that I'm not able to use my webcam because it's creating some disturbance on the audio channel. Okay, so I'm going to talk about the dual active bridge converter, and I've organized the material in 3 lectures. In the first lecture, I'm going to talk about the basic topology and its operating principles. In the second lecture, we'll look at the converter design, how we can optimize the design parameters to get best performance. In the third lecture, we'll look at some variations of the dual active bridge converter, introducing PWM control and some topology variations also. So this is lecture 1 about operating principles. Now the motivations for this type of converter which the dual active bridge converter is are as follows. We want a DC to DC converter which will give us soft switching without adding any auxiliary components. So we want to get soft switching, but we do not want to add any additional L's or C's or switches. We want bidirectional power flow from input to output and the other way, and there should be a need for a transformer, either motivated by a need for galvanic isolation, or if there's a high conversion ratio, so that the transformer helps you utilize the semiconductor devices better. There are 2 points I want to touch upon briefly before we go to the topology, because the topology follows from these 2 basic points. One is the mechanism for soft switching in bridge type converters. So as you may have already seen, in load resonant converters, which are basically a bridge converter followed by an LC tank, the way we can get 0 voltage switching for the switches is if the current output of the bridge lags the bridge output. So when you change the polarity of the bridge output, the current polarity remains the same, and the lagging current discharges the parasitic capacitance at the node which changes polarity in voltage, and that is what gives you 0 voltage switching turn on. Once you're able to get 0 voltage switching turn on, then you can add lossless snubber capacitors directly across the switches, and that'll help you get 0 voltage switching turn off also. The second point is about power flow between AC buses. So here we are looking at just an AC system with two buses connected by a predominantly inductive line, and we see the phasor representation for the voltages and the impedance. The power transfer between these 2 buses is given by this expression here, and the things to note here are one, that the phase difference between the 2 buses is what's predominantly controlling the magnitude of power transfer via the sine phi, and also the polarity of the phase shift determines the direction of power transfer. So with the polarities as indicated here, if phi is greater than 0, then we have power transfer from left to right. If phi is less than 0, then we have power transfer from right to left. One more thing to remember is that in the system, the current is lagging out of the voltage sources. So this is tying back to our discussion of soft switching, and we'll see that in the next slide. So this is again a repeat of the diagram we saw on the last slide. we start with a 2-bus AC system with sinusoidal voltage sources, and we then replace these sinusoidal voltage sources with square waves, high frequency square waves, and then we go ahead and implement the circuit which will generate these square waves. So the DC source followed by an H bridge, and you can use the H bridge to generate high frequency square waves at the bridge output. We do that both at the primary and the secondary side, and the impedance here is replaced by the impedance L here and a transformer. This impedance L will also include any leakage that this transformer has. So this is one way to look at how the topology can be derived, starting from the simple case for the AC system. I'm not sure if it was actually derived like this originally, but it illustrates the two basic operating principles of this converter. The fact that the power transfer is controlled by the phase shift, and that we have lagging current which gives us zero voltage switching for the two bridges. So here we look at some of the operating details. To generate the square waves from the primary and secondary bridges, we operate all the switches with 50% duty ratio, and we turn on the diagonal switches simultaneously. So S1 and S4 turn on simultaneously, S2 and S3 turn on simultaneously. So and produce a square wave here. Now the square wave produced at the primary and the secondary are phase shifted by angle phi, and that's easily achieved by simply phase shifting the turn on for S1 and S1S by the same phase angle phi. Now once we know that Vp here is a square wave and Vs here is a square wave, we can now reflect Vs to the primary, and we again have a square wave just scaled by the turns ratio of the transformer. The difference between Vp and Vs prime then is the voltage across this inductor L, and looking at the different values of Vp minus Vs, we can then determine the inductor current IL. So we have four possibilities. We could have Vp positive or negative, and we could have Vs positive or negative. So in one case, when the voltage across the inductor is VDC1 plus VDC2, we get a sharp rise in the inductor current in this region where the inductor current is rising from minus IL0 to IL1. Then we get in this region we get voltage across the inductor to be VDC1 minus VDC2, so the inductor current rises from IL1 to IL0, assuming that VDC2 is a little bit smaller than VDC1. And then we have a similar operation in the other half cycle, just with a negative polarity. So the current ramps down sharply first due to negative VDC1 plus VDC2, and then it ramps down slowly due to negative VDC1 minus VDC2. Okay, so we said that we are going to get soft switching because the bridge output current is lagging the bridge output voltage. Here we are looking at one transition to see how it's actually happening, so we focus on the transition for the turn on of switch S1, which is also the same as the turn on for switch S4. We'll just look at waveforms pertaining to S1. So the transition starts when we turn off S2, the complementary switch of S1. So you can see this blue waveform here. VG is the gate source voltage of S2. We are pulling it low. As soon as we do that, the current which was flowing through S2 now starts flowing in any capacitor which is present at this node. So all of this current IDS S2 transfers to IC, which you see, this is the blue or purple waveform in the lower graph here. And when that happens, this starts charging the node up towards VDC1, and the voltage across this switch S1 starts reducing. So the green curve here in this graph, you can see VDS S1 is slowly reducing because of the current in the inductor. Once this node reaches VDC1 and the voltage across this switch goes to 0, then this inductor current, which is negative out of the bridge, starts flowing in the anti-parallel diode of S1. That's the current you see here. This is ID1. So once VD S1 goes to 0, the current from the capacitance transfers to the diode, and while it's still flowing in the diode, we turn on S1. So you can see this is the red curve here in the graph, the gate source voltage of S1. When we turn on S1, then the current transfers from the diode to the switch S1, and because at the turn on instant the drain source voltage was already 0, we get 0 voltage turn on. The transition for S4, as we said earlier, is identical to S1. The transition for S2 and S3 are also identical to S1 and S4. We just have to look at the other vertex. So instead of looking at this vertex, we will now be looking at this vertex for S2 and S3. The transitions for the secondary side bridge are a little bit different but similar in nature. So for the transition for S1, we have to look at this current vertex, and for the transition for S3, S3S, we have to look at this current vertex here. Okay, so that's as far as the soft switching details go. The current expressions for the inductor current, we can derive these vertices IL1 and IL0. The derivation is quite straightforward. The important thing to realize is that if we are in steady state, then this current is minus IL0, same as this current IL0 at this vertex, only reversed in polarity. So now we know that the current ramp during this time period phi is IL1 plus IL0, and that's happening because of VDC1 plus VDC2 prime across the inductor L, and the current rise across in this time period pi minus phi is IL0 minus IL1. That's happening because of VDC1 minus VDC2 prime. And once we have those equations, we can solve for IL1 and IL0. So here I'm listing the expressions, and I'm trying to hide some of the algebra and just exposing the important aspects. The important thing to note here is that this part I base is essentially a constant depending on the the input DC voltage, the value of VDC1, and the impedance of the leakage of the inductance L at the switching frequency, and the remaining part of the expression depends on the phase angle phi and the value of M, where M is the ratio of the of VDC2 prime to VDC1. So VDC2 referred to the primary side divided by VDC1. And what this tells us is essentially when IL0 and IL1 will be positive. We need that for zero voltage switching, and we can now derive conditions for IL1 and IL0 to be positive based on the phase angle phi and the ratio of the input and output voltages. The power transfer in the converter can also be derived now. Once we know the vertices IL0 and IL1, the power transfer is essentially given by the voltage output of one bridge, of the primary side bridge, multiplied by the current output of the bridge averaged over one switching cycle, and that's identical to what you would get in half a switching cycle because of symmetry. So it's easy to see what the power transfer is going to be looking at these voltage and current waveforms. So Vp for this half cycle is just VDC1 and this is the current output of the bridge. So we're going to multiply VDC1 by this current and integrate over this half switching cycle. Because VDC1 is constant, what we essentially need to do is compute the area under the inductor current waveform. So essentially the power transfer would be given by the positive area under the inductor current, which is A1, minus the negative area under the inductor current. So the thing to realize here is that because the lagging current A2 during this time period, which is denoted by this red triangle, power is actually flowing back into the input. So the net power going out of the bridge is A1 minus A2, and once we know these vertices IL1 and IL0, then we can go ahead and compute A1 and A2, and using this formula then we can derive the power transfer. After we simplify the algebra, the expression is a very simple one. Given here, it's parabolic in nature, and we are again hiding some of the algebra in this P base, which is defined as VDC1 square divided by the impedance of the inductance at the switching frequency. The maximum power transfer is achieved at pi over 2, and looking at the expression, it's clear that the polarity of phi controls the direction of power transfer. The power transfer is very similar to what we would get if we did a fundamental component analysis. So what we could do is replace these square waves Vp and Vs prime by their fundamental component at the switching frequency, and the inductance by its impedance at the switching frequency, and then we can derive the power transfer as in the 2-bus AC case. And we come up with this expression. Now this is a sinusoidal variation, but in actual value it's very close to this parabolic variation we get for the converter, and this is illustrated in the figure here. So both for positive and negative phase shift, the exact value of power transfer is very close to what you get when you just do a fundamental component analysis. Now the inductance L is a very important parameter in this converter. We would typically utilize the leakage inductance of the transformer to realize this inductance. However, in a well-designed transformer, the leakage inductance is usually not large enough, and we either have to add an external inductor, or we have to think of another way to incorporate the inductance or increase the leakage inductance of the transformer. So this picture here on the right is one possibility for a high leakage transformer. Here what we are doing is we are intentionally adding a leakage flux path. The center limb of the core is providing a path for flux to leak between the primary and the secondary. So some of the flux from the primary will go and return through the center limb and not link with the secondary, and therefore this center limb will actually give you a series leakage inductance in the transformer. The good thing about using this kind of structure is that now we don't have an additional component, and also we would typically have a lower loss in an integrated structure as compared to discrete realization of transformer followed by an inductance. Just to summarize now, the key features of the dual active bridge are as follows. It comprises of 2 H bridges. It has a very symmetrical structure, and we are able to get bidirectional power flow. There is no inductive filtering in the converter. The power transfer between the 2 DC buses is controlled by phase shift. This is similar to the 2 AC bus case. We have lagging current in the bridges, and therefore we are able to get zero voltage switching. Because we don't have an inductive filter, we are able to get a single cycle response in the power transfer. So that's the end of lecture 1, and next time we're going to see some of the converter design details, how we can optimize different parameters of the converter to get best performance and minimize the size. Thank you.